Asphalt Modifiers and Rejuvenators from coal-derived chemicals. Jeramie, look forward to you giving this thing. You're from WRI too, right?
Yes.
Yeah, good.
Here, the School of Energy Resources, they've gotten money from the state to begin to look at alternative uses for coal. And so I'll explain why this is important. Also, I just want to mention the other folks on the team at WRI, JP, who just spoke. Sure, what's happening with coal? Most people kind of know what's been going on. It's been in the news quite a bit. Coal production has been declining for the last several years, and there are several reasons for that. One, it happens to be the abundance of cheap, clean, relatively clean fuel of natural gas. Also, intermittent renewables have becoming, this is maturing as a technology. There's a lot of policies in place. It's been growing. I heard last summer in California that something like 60% of their energy is coming from intermittent renewables. So, there's a decrease in demand for coal on the economic side, and that doesn't say anything about the environmental pushes that are behind it. We'll talk about some of that later. So, in the last election, this was an issue that people kind of played on and said, well, we have a decrease in production, and so we're losing also jobs in the United States, especially for those for coal miners. So this is an issue, but jobs have been growing in other sectors as well. For the state of Wyoming in particular, this is an issue. So this plot just shows the largest coal producers in the United States, and you can see that Wyoming is way up there. We're the top. We produce hundreds of millions of tons of coal a year. And so the most recent numbers I could find was in 2018, we produced 304 million tons of coal. And so I want to just put this number in perspective for you. So the United States has about 330 million people. So every year we could potentially dig up 1 ton of coal and deliver it to you, every man, woman, child in the United States. So it's going to be pretty hard to find something else to do with coal on this kind of scale. Obviously, this is, we've had this decline for more than 10 years in coal production in Wyoming. This has led to a number of economic effects for the state. We've had a number of energy and coal-producing companies that have filed bankruptcy and some that have left the state. So these are some of the recent ones. There's a few more since then, but in the summer 2019, there were 2 major ones. Also, there's a large environmental and social push to basically do away with coal, especially thermal coal for coal-fired power plants for energy. And so, ex-Mayor Bloomberg wanted to help, put the nail in the coffin of using coal for energy, thermal coal. So he would like to see it gone by 2030 altogether, coal-fired power plants. So we generally think of coal, and the major use of coal is generating energy. And this is true for today, and that's basically due to economic reasons. But this is now changing. But in the past, there's always been other value to coal instead of just burning it, consuming it for energy. So this is a coal products tree. So basically, we have these different branches. You can't read any of this, but there are different branches that come off about the gas and the oil and the different things that can be made, and the different products that can be made from these different streams. So there's quite a bit of things that can be made. This graphic kind of simplifies it a little bit for us, shows a couple major ones. Some things that are up there that you may not have been aware of. You see on this tree kind of in the lower right-hand corner, you see nylon. Well, during World War I, nylon was made primarily from coal. So there's a variety of materials and polymers, chemicals, and different things that can be made from coal. So the one thing I want to point out for coal is that although thermal coal for energy is declining, certain grades of coal and their use are increasing, and these are high-grade coals to make metallurgical-grade coke. Metallurgical-grade coke, in this one graphic here you see steel. Well, metallurgical-grade coal is used to make metallurgical-grade coke, which is then used in blast furnaces to refine iron ore to make steel. So there's not very many replacements of the material that can replace metallurgical-grade coke. It's continuing to grow in its utilization there. So there's you know, there's a variety of things that can be done with coal. And because of economics, don't know what happened here. Is that something I can do? Okay. All right. You know, a lot of these products from coal went away, especially when petroleum refining came on board and the large volumes and volumes of scale and all of these things. But maybe it's time to go back and look at some of this. So the state, with the University of Wyoming and School of Energy Resources, is looking at different methods and ways to optimize the amount of molecules and the type of molecules that we can get out of coal. And so there's this thermochemical pathway, so trying to marry different ways of processing coal to really maximize. This is being evaluated pretty much only on Wyoming coal, since the state is paying for it. And trying to identify what kind of pathways are going to maximize the molecules that we need for certain products in certain markets. And to set up in the next few years to start making products. So when we talk about thermochemical, we're talking about, on the thermal side, basically pyrolysis. So we just heat things up until we start to break bonds, and we can get some chemicals made here. There's all kinds of derivatives. We can do this with co-processing streams of different liquids, perhaps. We can use gas, we can use hydrogen, we can use methane. We're also a very methane-rich state. We can use catalysts. We can do all kinds of things. So we can really change the properties of the molecules that we get. Also, on the chemical side, we can do different types of solvent extraction. A lot of these solvents have a tendency to react with coal and maybe donate hydrogen or do different things to the coal. And again, there's all kinds of derivatives here, temperatures and solvents, reactivities, everything. The other thing that's being investigated is to do what is called the dry methane reforming. So this is a method to take CO2, we can capture it from combustion or from other things, or maybe it's generated when this all gets worked out in the exact model and the backbone that goes into the coal refinery. Maybe we can capture what's being made there and combine this with methane, since we're also a methane-rich state, and produce what's called synthesis gas. Synthesis gas is useful. It's used in Fischer-Tropsch processes usually. We can make waxes and alcohols and different things. So really the idea here is let's maximize the value of everything that we can get out of coal. All of the liquid parts, all the solid parts, all of the gas parts and everything. So there's all kinds of products and applications that have been investigated. These are kind of the main ongoing ones that have been identified through this program. Obviously, there's a lot of molecules that can be made that can be fed directly into traditional petrochemical refinery infrastructure and can be utilized there. Synthesis gas, there's a lot of applications for resins. These can be things like that may go in like epoxy coatings or for different industries. Also, there's a big emphasis on making different polymer coatings, and also paving asphalt and roofing asphalt, and that's why we're here to talk about this. There's also some advanced carbon materials, carbon fiber mats, graphene oxide. Also, in the end, whenever you process coal or even petroleum, if you do a delayed coker, there's always some carbon that needs to be rejected somewhere. And what do you do with this solid carbon? Well, soil amendments, building materials, different applications like this. So the whole goal here is to basically create the smallest carbon footprint that we can, and hopefully zero, and maybe even turn it positive. So why Wyoming? Obviously, you know already that we produce the most coal in the United States, but cost is a driver. So Powder River Basin coal is about $12 a ton. I don't know that you can purchase anything on the planet at that price, okay? So it's extremely cheap material to start with. And so you have a lot of room now to play, to modify and do chemistry and do other things to make different products. So we have vast reserves, okay, 42 billion recoverable tons, easily recoverable tons, and there's relative consistency in the different seams of this material. So it's we wouldn't be subject to, you know, crude oil variability per se. Also, our coal is just kind of a special kind of coal. It's not the highest ranked coal, but it's what's called subbituminous coal. Subbituminous coal gives us a lot of kind of interesting chemical handles that we can modify further. And also on the state side, of course, we would like to have full employment. We'd like to create more technical jobs, and we would like to export products. increase the revenue for the state. So this nice map here shows the different kind of grades of coal that are available and where they're located in the United States. And you see Wyoming has got a huge, vast amount of the blue stuff, which is the sub-bituminous coal. And it's important for a lot of reasons. So one of the things that may have, some of the people that have been around a while, they have maybe heard coal, and so they immediately went and began to think about coal tar pitch and some of the practices that were done, before about the 1960s in the United States and other places in the world. Coal tar pitch is infamous for having a lot of carcinogens in them. So these are polycyclic aromatic hydrocarbons, PAHs. Also, this has been studied, obviously, in asphalt and roofing materials, and both materials have their own different carcinogenic classifications, paving grade being lower. And there's been several studies looking at the pH levels in a variety of bitumen or asphalt across the world, and essentially this nice table here shows some ranges of pHs. So if we take the high level on these materials, we can say maybe that's about 110 ppms of PAHs. The other thing is, the guidelines and restrictions on pHs are getting tighter and tighter everywhere in the world, especially Europe and in the United States. Coal tar pitch, different derivatives have been used for different applications and different sealants, like crack sealants or foundations, or for roofing type of applications. And so this is just one recent example I had pulled off the internet for us, where in Washington, D.C., they had created this act saying that we need to be below 1,000 ppm if you're going to use any materials, and specifically looking at coal-based or coal tar-based materials. So this is just a nice diagram showing the different molecular structures of some of the pHs that are tracked whenever the EPA has standards and they want to know, how much pHs are in your food or in water or in soil or whatever. These are some of the molecules that they're looking at. So where do pHs in coal come from? So the one thing I want people to take away in this talk is that what we're doing is not the old traditional coal tar pitch stuff that was done long ago. We're doing something that's completely different, and we don't have much PAHs. So I just want you to understand that right away, because this is a big hurdle for people whenever we talk about coal and coal utilization in products, and especially in asphalt. So there are two main ways that you're going to get the PAHs, and they're actually both processes. One's a process on the geological time scale, and we'll call it the source, and the other one is the immediate processing that we may do in a laboratory or refinery. And as was mentioned earlier, speaking about the graphene and the graphite, basically the earth is a nice reactor. The earth's crust, we have dead material that goes in, and it can be subjected to heat and pressure and time, and it can undergo various reactions. So it has a very long time to do this. And the longer the material sits in the Earth's crust, the more chemical transformations occur. So here are some different kind of grades of coal. So we can think of very low-rank coals like the peat and the lignite, and then very high-rank coals like anthracite, which is glassy. It's starting to approach graphite. Lignite is 20 to 35% carbon. There's a lot of oxygen, a lot of other material in there. And anthracite is more than 80% carbon. So basically this is the maturity of the coal just being left in there. Its crust longer and longer, it becomes more aromatic. And here's kind of some more molecules that might help us understand that. So low-rank coals, if we think about lignite, basically it looks like dead, it looks like biomass. We still have a lot of lignin and cellulose type structures, and a lot of single aromatic rings, and a lot of oxygen functional groups and other alkyl groups hanging off from it. As the material matures, going across here and down to the bottom in the anthracite, it becomes more aromatic over time, has more time to react in the Earth's crust. So what was done in the past to make coal tar pitches was using basically this low volatile bituminous coal. It's fairly aromatic on its own. Okay, so if you break it apart, you're going to get some highly aromatic fragments out of it. And the work that we're doing, we're using subbituminous coal. We don't have a lot of conjugated large aromatic molecules in there. And if there are aromatic molecules, they're highly substituted. We have all kinds of oxygen functional groups. We have different alkyl functional groups. So already we're dealing with a different material. When we think about on the process side, the other thing we need to realize, coal tar pitch is made primarily as a byproduct from refining of steel, but it's really to get the metallurgical grade coke. It's not during the steel process, but you have to make your metallurgical grade coke that goes into the blast furnace to refine your steel. So this is what happens to coal, metallurgical grade coal, to make the coke for the steel industry. So you put it in a furnace, you cook it to about 1,000 degrees C, and then you get off some liquids, and then you take these liquids, that's the tar, you distill it, and you get your coal tar pitch. So as you can imagine, at these high temperatures, you're blasting apart the molecules, you're lopping off any side chains, oxygen functional groups, all this kind of stuff. So you're going to end up with a very highly aromatic material. Again, this is not anything unique to coal tar. Get some feedback here. Coal tar pitch. But it's something that we all have experience with because most of us eat cooked foods. And if you cook your food a little bit too long and you start to char it, you can begin to do these reactions in your kitchen or your barbecue grill and start to make low levels of PAHs. Okay, so this is something that it's kind of ubiquitous. It's everywhere. Just to be aware that it's not just coming from coal, and coal is the worst thing in the world because you get PAHs. It's something that's all over the place. So pyrolysis kicks in around 360 degrees C, depending on the material. But this destroys bonds and it promotes aromatic condensation, and so you begin to make more and more aromatic materials. So with the University of Wyoming and the state, we're investigating methods to extract molecules from coal at below pyrolysis conditions. So we're going to stay away under 360 degrees C. We can extract a large amount, 30-60% of the material with solvents. We can do different things in different separations. We can use temperature, for example, and collect different fractions. And so we get these low PAH, high oxygen containing molecules. So here's some data just to try and convince you that we're not making coal tar pitches. So on the left-hand column, these are some of the PAHs we've measured in a traditional coal tar pitch. If you add all those up from just those ones we measured, that's 12 weight % of coal tar pitch is these PAHs. So this is a lot of PAHs. In the different solvent fractions from what's being done at the university, you can see we just neglected naphthalene when we did the totals here because naphthalene is something that's coming from the process. We can get fractions now that are down to 10 ppms and then some fractions that are down to, we can't even measure the PAHs. Okay, so we don't have environmental health and safety issues from using this material. Also, the other thing I want to point out, there's a lot of information here, but just look at that column that says oxygen. So depending on the solvents and the temperatures and how we fractionate this material, we're always going to get material that has a high amount of oxygen. That's just because we're starting with a high oxygen feedstock. It's subbituminous coal. So from 5% up to 15% oxygen. Now, if you understand asphalt oxidation and what happens chemically there, you may say, oh, I don't want to put this material in asphalt because of all this oxygen. Oxygen functional groups, especially the ones that have OH bonds, can really be detrimental to asphalt because as these build up, they're great at absorbing to the rock interface, but then when you get water in there, water will tend to displace those from the rock interface, and this is where you get your stripping and your moisture damage. So that doesn't look good. And also, these oxygen functional groups can lead to hydrogen bonding and can create structures of these molecules now, which can impart, rigidity or brittleness and can lead to cracking. And also compatibility issues. It's highly polar. It will want to come out of the non-polar asphalt matrix. So this is where chemistry comes in to help us address some of these issues. So this red molecule here is a hypothetical molecule from one of the fractions. We've done mass spec, we've done elemental analysis, functional group analysis. We've done all kinds of things, and we know kind of what the generic structure of some of these molecules are in some of these fractions. We can take these molecules then and we can apply basic chemistry. So here we're doing esterification. Esterification is very commonly used. It's used in large scale materials. Think about your treated lumber for your fence at home or your decking. You know, also aspirin is made through an esterification process of phenols. So this is very common. If we can apply these chemistries, then we begin to address some of the drawbacks we have to this feedstock. So we can increase the solubility and compatibility with asphalt. And here's just an example here. On the vial on the right-hand side is the material before we do any chemistry, and this is in toluene. It's not soluble at all in the toluene. I don't know what I'm doing here to get feedback, but if we do this chemistry and do esterification, then we produce a material that is now completely soluble in toluene. And so this now is going to have good compatibility with asphalt. Also, we get rid of these OH functional groups, then we remove any detriment from moisture damage. But we can begin to engineer those groups because some of the anti-strip agents are actually like phosphonate esters or different esters or amines or different things like this. So we can actually engineer in here some adhesion promoters now. Also, we can enhance upper temperature, lower temperature PG performance, and this is completely unproven, but it's a possibility that we need to look at further. There may be some possible antioxidant effect from some of these materials, or at least they might work to dilute or reduce the aging in some way. So this has been our challenge, to take this powder, which we get here, which is a high melting, highly polar solid, and turn it into something that will be compatible with asphalt. And we can apply some chemistry, and lo and behold, we can produce material like this. This is material that was just scraped out of the vial and put on the weighing paper, so you can see. Now we have material that has good compatibility with asphalt. So just to also make a point about the chemistry and what kind of opportunities we have here, because we're starting with a material that now we can engineer. We can take a bottom-up approach and make it kind of the way we want, give it the properties that we want. Because we're starting with something so cheap, we have a lot of room now to play with the chemistry. So the squares here, these are low temperature properties of different blends. So we have a Wyoming base asphalt, and then we put 5%, 10%, and 20% of our material in here. So the squares are the material that has no chemistry applied to it. And basically, let's just look at the blue line here. The red line is the S value for the low temperature. It's not really changing very much. But let's look at the blue line, which is the M value, which has to deal with the relaxation. So the squares show, if we don't do any chemistry, we get this huge jump in the M value. I mean, this is ridiculous, right? This is just horrible. And then if you do you subtract your S and your M, and you get your delta TC, you see your delta TC just, it falls off the cliff. JP talked about he likes the competitions of breaking records. We can break whatever record, I think, here. So now, if we apply a little chemistry and we do a little esterification, we put on a few alkyl groups through the esters, now we get a situation where we have these stars. Now you see we have a less dramatic increase in the M value, and now our delta TC is increasing. So this is a strategy now that we understand very well. We actually understand it well from vis breaking, kind of going backwards now. But we know how to engineer our materials now to improve the low temperature properties. Oh, and let me see here if I can go back. The one thing I do want to point out real quick is you can see also how the upper temperature PG changes dramatically with this material. So basically, by adding 20 weight percent, we can increase the upper PG by almost 30 degrees. So it has a huge effect on the upper temperature. We know if we bump up that upper temperature, we could have some problems in the low temperature region. So that's, we're focusing really on that low temperature region. Here's one example of a success. So this is a coal material. It was isolated by a different method. It was esterified and using a different chemistry. And here, if we take the material without doing any chemistry, it's not compatible, it doesn't blend with the asphalt. It's completely insoluble. It looks invisible. It doesn't change the properties very much at all. If we take the esterified version of it, blend it in with the asphalt, all of a sudden it's soluble, it's compatible. We increase the upper temperature. We decrease the low temperature, we improve delta TC, and we make a good product. Okay? The other thing that we're looking at is that we do tend to make some more soluble oils when we do this, these chemistries. Can this oil be used for other things? Well, it can actually be used as a rejuvenator for recycling. So we're breaking our products into two different classes. One that's going to modify the upper and lower temperature performance grades, and then another class of more soluble type of softer oils that can be used for rejuvenators. So here's some data. If we take AAD and the agent in the laboratory, you can see what the different properties are there. If we blend it with our heptane soluble portion, we see that we lower the upper PG, we lower the low temperature properties, we improve delta TC. We do everything that we would like to ask from an additive as a rejuvenator. So, you know, we've had some successes along the way. We still have a lot of work that needs to be done. Part of it is to help the public perception of what we're doing and using coal as a material. But, you know, coal potentially can provide a low carbon footprint asphalt product. Okay, we don't have to distill it and do a whole lot of things to it and pyrolyze it or do anything to get these materials. So they can be used as maybe someday as an asphalt replacement, but certainly as additives to supplement petroleum-based asphalt products. This is important because asphalt, as we know, is the most recycled material, and if we need to put material in there, additives that are going to be compatible with future recycling campaigns. Okay? So the thermochemical processing gives us a lot of knobs that we can tune the chemistry, we can tune some of those pH content, we can do a lot of things to try and make the best products that we can. And, you know, I already mentioned low levels of pHs, but the one thing that excites me about all of this is that we have this large feedstock that's relatively consistent. And now we can be in charge and we can drive how we want to make our products. So if you have certain properties that you're interested in evaluating, we have the potential now, because this is so cheap, we have the room to play on the chemistry side, we can begin to engineer materials. Okay? So we're not at the mercy of, you know, who's buying what and trading what, and how are they processing it, blending it, and doing all these things. And so obviously there's a lot of ongoing work that needs to be done. We'd love to continue to partner with some other folks in the industry to help achieve some of these goals. So if you have things in mind that you would like to pursue, we're completely open to this. And I need to thank all of these people here. So on the University of Wyoming side, we have some folks, Dr. Richard Horner, who's really kind of the director of a lot of these coal refinery projects, has been supporting us, helping us, funding us. Also some professors here at the University of Wyoming who have been providing some of the samples and doing the processing of the coal. We're doing some ourselves, but they're doing the bulk of it. Brian Leonard in the chemistry department has been very pivotal person because he helps me get my University of Wyoming postdocs, and various other people. And then we have a whole team behind us at WRI. So we have mixtures of chemical engineers, chemists, technicians, civil engineers, and everybody that works to help make these projects a success. I'm not sure. I guess I didn't do too bad on time. I just want to show this just as an illustration. So this picture comes from 1957. So this is the crude oil products tree. You can see there's a lot of material there. But if you look in the arrow on the left-hand side, this says this is what the crude products tree looked like 60 years ago. So this was at the turn of the 20th century. We had three products. We had, can't read them, but it says black oil, kerosene, and gasoline, you know? And then, so 60 years later, we had this beautiful tree with all these products, and now even today, as Pavel pointed out, refineries and the push to make chemicals and away from fuels and all these things, now the tree is even much more complex. So we're kind of going up in this direction again, hopefully with coal as a material. So it's a valuable national resource, and we have a lot of it, and I think it has a lot of potential. So that's all I have.
All right. Thank you, Jeramie. One quick question from anybody? No? Yes?
I grew up in Pittsburgh, so the natural question is, are our friends in the East doing the same with anthracite?
So, yeah, we're not unique. There are many programs, private companies, and kind of consortiums and agglomerations of state agencies and universities, both on the East Coast and the West Coast, all looking to do this. Oakridge National Laboratory, we're Western Research Institute, University of Wyoming, our partner with Oakridge National Laboratories on a lot of the initiatives that they're doing to make different coal-based products. It's a huge thing. DOE opened up a funding opportunity announcement last year, basically to look at different coal products. Asphalt hasn't made it on the radar yet, but we've been in discussions, and hopefully it will show up there as well. So, yeah, there's a lot of activity all over the place. A lot of neat things. Even companies that are building kind of portable standalone nuclear reactors, are looking into using the heat off from those to drive the processing of coal to make products. I mean, it's happening all over the place in a lot of creative, interesting ways. The products, though, is something that is really the sticking point. People are struggling in a major way to understand how to make high-volume products that will compete with other products out there. So it's really coming down to the products and the volume and different things.
All right, thank you, Jeramie. 10 minutes or so, maybe 15, so 20 after, come back. Thank you, Jeramie.